All right, in a previous video, I talked about the center and spread for the sampling distribution of the sample mean. We discovered that the mean in the sampling distribution is the same as the mean in the population, and the standard deviation in the sampling distribution is a fraction of the standard deviation in the population. All right, so now we're left with the question of what about the shape of the sampling distribution? In other words, can I answer this question? X bar follows a certain distribution. What would that be? So for instance, is this going to be uniform? So would we expect, if we were to draw a histogram with the based on our sample means, would it look like this, like a rectangle? Would we get a bell-shaped distribution? Maybe it'll be right skewed, or maybe it'll be left skewed, or some other distribution. It'd be nice if we knew the shape. We know the center and the spread, so let's see. There are two scenarios to consider here, and we'll call one of them our best case and the other one a next best case. So in the best case scenario, if the population distribution is normal, in other words, you have some random variable x, it's normally distributed, and you know its mean and standard deviation. If that's the case, the population distribution is normal, then the sampling distribution of the sample mean is normal. In other words, x bar will also be normal. And we've learned previously it'll have the same mean as we find in the population, and the standard deviation will be sigma over square root of n. So let's consider an example here where I know that the random variable x is normal. It has a center at 100 and a standard deviation of 20. And I'm going to take samples of size 16. And I'd like to know, what can I say about the distribution then of the sample mean? Well, it's going to be normal, also centered at 100, but the standard deviation will be 20 over the square root of 16. In other words, 20 over 4, which would be 5, so this equals 5. So in the population, I'm seeing a bell shape with 100 in the center, and each standard deviation is 20 units, so this would be 120, 140, and 160, and on the left-hand side we'd have 80, 60, and 40, and then we can apply the empirical rule and say that's 68% of values and so forth. Now, the sampling distribution of the sample mean has the same center, but it's going to be a lot skinnier and taller because the standard deviation is so much smaller. So it's still centered at 100, but the standard deviations are just 5. So just know that if you were to draw them on the same scale, this distribution is still bell-shaped, but it would be a little bit more compact. But I'm just going to draw that over to the side with my kind of standard bell-shaped curve and say that this is going to be centered at 100. And each of these standard deviations now is just 5 units. So this is 105, 110, and 115. And this would be 95, 90, and 85. So in the population, 68% of my values are between 80 and 120. In the sampling distribution, 68% of my values are between 95 and 105. So it's really important that we make this adjustment to the standard deviation if we're talking about the sampling distribution of the sample mean as opposed to the population distribution. So that was our best case scenario. Now let's consider our backup plan. So the next best case. So if the sample size is sufficiently large, and it turns out that that just means our sample size is at least 30, the sampling distribution of the sample mean x bar is approximately normal. And this is regardless of the shape of the population. So it could be normal, but it could be uniform, left skewed, or right skewed. So this is a very powerful statement. It's called the central limit theorem. The central limit theorem. I want to just highlight that. So if you don't know the shape of the population distribution, or if in fact you do know it and you know that it is not normal, that's okay. Just make sure your sample size is at least 30, and then you'll end up in the same place, knowing that x bar is normally distributed with a mean mu and standard deviation sigma over square root of n. That's their standard error of the mean, just as a reminder. So the end result is the same. So the bottom line is, if we want to know that our sample mean follows a normal distribution, we either need to know that the population is normal or that our sample size is at least 30. Now, if we cannot confirm either of those two things, well, then we're just going to, as far as this video is concerned, we're going to stop. So this would be neither. So the population is not normally distributed, and your sample size is less than 30. There are other techniques that are beyond the scope of this lesson and video, so I'm just going to say we would just end there. All right, so but let's say that we are able to proceed. Let me do an example. So let's say that you have a mean of 64 and a standard deviation of 18, and you're taking samples of size 9, and we don't know. Actually, let's make and we don't know the shape of the population. Well, in that case, because our sample size is small, we'd have an issue. If I don't know anything about the shape of the population, with this sample size, it's problematic. So I'm going to actually up this and say, well, what if I take samples of size 36? So now I'm going to meet this threshold, and it's going to be safe for me to work under the assumption that x bar is going to be normally distributed with a mean of 64, same as in the population, but the standard error of the mean will be 18 over the square root of 36. Now I'm choosing numbers where it's easy to take this the square root, so this would be 18 over 6, so this would just reduce to 3. So I know that my sampling distribution looks like this. It's centered at 64, and this would be 67, 70, and 73, and this would be 61, 58, and 55. Now, knowing this, I can answer questions such as, what's the probability that I would get a sample mean of less than 62? Or the probability that I would get a sample mean of more than 65? Or the probability that I would get a sample mean in between 59 and 69. Or, which sample mean corresponds to the 90th percentile among samples of size 36. So these are going to be questions where, excuse me, grab my calculator. The first question here, where I want to know the probability that I would get a sample mean less than 62. Let's see, I'm going to use my distribution menu. That's a normal CDF question. So less than 62 is somewhere from here over. And so the left bound is negative infinity, so I'm going to use negative 10 to the 99th power. The upper bound is going to be 62, and I forgot my comma there, comma 62, comma. The center is 64, and the standard deviation here is 3. That's the standard deviation in the sampling distribution. So that is about 0.25. Now, greater than 65 would be over here, and that'd be this area to the right. And that's another normal CDF function with 65 as the lower bound. I'm going to use 10 to the 99th as my upper bound. Again, 664 and 3. And that's about 37. Now, what about between 59 and 69? So that's the easiest one on the calculator. I use 59, 69, 64, and 3. And that's 0.90. So between 59 and 69, so that would be between 59 and 69, that'd be all of this in between. And it makes sense that that's quite a bit of the area under that curve, so I'm not surprised I'm getting 90% now. The 90th percentile, as a reminder, what I'm looking for when I say the 90th percentile is the cutoff point that separates the bottom 90 from the top 10%. So what would be the sample mean that would do that? So this is an inverse question, so I'll go to my distribution menu and option 3. So the area over here that's to the left is 0.9, and the center of this distribution is 64 with a standard deviation of 3. So the value that would do that would be an X bar of 67.8. So somewhere, about over here, there would be 90% to the left. All right, so that's how we can. That's the basics, I would say, for the sampling distribution of the sample mean. In the next video, I'll show you some application problems. I hope you'll join me.